We finished up the last lecture with a comparison of RLS versus an LMS, and we saw that the RLS adapted to the new weights very effectively, and the error went down much faster than it did with an LMS. I was having some fun playing around with this a few years ago and trying to see how things performed. I added some noise to the signal and I ran it for more samples, 20,000 input samples. The NLMS, with the beta that I chose, adapted well to the weights and relatively quickly, but it had some misadjustment error, and you can see that in the plot on the left. The red are the estimated weights, and the blue underneath them is the actual weights, and it's a little bit off. But you can see that the error went down and it stayed near an error floor that is due to the noise added to the desired signal. I ran the same test with my RLS filter code, and I got the following. I didn't notice it first, but first you should notice that there are no red lines anywhere. Something happened to the weights. They're gone. Next, it's only plotting up through about 14,500 samples instead of up through 20,000. So what's going on here? At this point, we get, in MATLAB, not a numbers, NANs. Clearly something's wrong. I checked the code, ran it over and over again, and then I remembered hearing someplace that the square root RLS filter is more stable. So what's going on that makes this unstable? To better understand, we can go look at our update equation for P. P, as you recall, is Rx inverse. So P n minus 1 would be Rx inverse at time n minus 1. And this has some nice properties. We know that it is positive, definite, and symmetric. However, if we have any round-off errors in the system, and when I'm running the RLS code, I was doing it in MATLAB using double precision floating point arithmetic, so the round-off errors should be relatively small. But any round-off errors in our updates and calculation may destroy the fact that we have now a symmetric positive definite matrix. I misspoke. Positive definite. Okay, so what can be done? We need to enforce that this is positive definite along the way. If, for example, it drifts just a little bit, it's possible that we could get a negative eigenvalue. And the larger the matrix, the more likely this is to occur, as changes in one place in this matrix impact all of the eigenvalues. If you have something that is no longer positive definite and no longer symmetric, then the error in this situation tends to explode, and we get the problem that we see here. So we're going to have to redevelop our RLS algorithm in a way that makes it more stable. We've seen how good this can be. It's worth coming up with a way to make it more stable. But unfortunately, it's going to require largely rebuilding this from the ground up and a little bit more complicated approach. To set this up, we're going to define a new quantity, gamma, and this is going to be very similar to the g that we defined in our previous development. And I'm going to go ahead and put a conjugate in there. We're going to keep track in this of complex situations, so we can do the whole complex development from the start. Many of our other developments we've been looking at the real case, and then maybe I'll throw the complex at the end, but this will be the whole story from the outset. Okay, if we have this, then we can come up with gamma inverse without too much imagination. And we should note that this is a real valued scalar. And now we can multiply that by g of n. G of n was defined in our previous development, and that gives us, in fact, let's go back and take a look. G of n is simply equal to something that's very similar to what we've just developed, but it has the p n minus 1 and the x of n at the top. Let's put that over there just as a reminder. So now we get lambda to the minus 1, or 1 over lambda, times p n minus 1 times x conjugate. So where did the conjugate come from? If we were doing the complex filter, we would have had a conjugate there and there. Okay? So I'm sure this gives you no idea about where we're going with this so far. That's okay, we'll get there in a minute. I hope it's okay. With these quantities to deal with, we're going to use those later as we develop. Let's talk about how we can come back to our original problem, which is how are we going to enforce that P is positive, definite, and symmetric. One of the ways we can do that is by construction. Since P is it's, I guess I should put here, actually, in the case going forward here, this is going to be not just a real symmetric, but it could be a Hermitian complex matrix. Since it is symmetric or Hermitian and positive definite, we can represent it with a Cholesky decomposition. There's nothing magic about this except that I'm impressed with whoever came up with it. Cholesky, I guess, obviously. But a Cholesky decomposition is essentially that we can represent P as a product of an upper triangular matrix with strictly positive diagonal elements times the Hermitian conjugate of that matrix. Let's make that. So we can think of this as essentially P of n is equal to P 1/2 of n times p to the 1/2 of n Hermitian. So the idea now is we aren't going to keep track of p, we're going to keep track of p to the 1/2, or the square root of p, which corresponds to our U Hermitian transpose. And by so doing this, anytime we need a p, we create it as a product, and by construction now, it's going to be a positive definite Hermitian matrix. So that's the basic idea. Now, let's go ahead and make things up to fit that. We're going to have to define something else. We're going to define a matrix, and this matrix will be something like this. Okay, so just to make sure everything's clear, this right here will be actually it's this way. This is going to give us a row vector. This will be a matrix. This will be a column of zeros. And of course, the 1 in the upper left is just a 1. And once we have this, just for completeness, let's go ahead and write down what this is going to look like. We'll still have our 1 here. We'll now have a row of zeros. And it looks like I need to put that over a little bit. And finally, the diagonal element stays the same. Okay, so I've copied down our A and A Hermitian for reference, and I've also copied down for reference our definition of gamma to the -1. And I'm going to do the hard work. Actually, it was done in the textbook. The hard work is just understanding what the textbook is saying. We're going to do the hard work of factoring this into a pair of matrices, also Cholesky decomposition type matrices. But these ones are constructed differently and written in terms of our gamma. Okay, to verify that this works correctly may take just a little bit of work. Let's go through and look at it now. So for example, if we take this row times that column, we get 1 plus the 2 lambda to the -1/2, so going to give us a lambda to the -1, or 1 over lambda. And then we have x transpose times p to the 1/2 times p to the 1/2 Hermitian. That will give us a p, and times x transpose n. So that gives us exactly this expression up here. on the bottom set of matrices, we get gamma to the negative 1/2 times gamma to the negative 1/2 gives us gamma to the negative 1, which is the same thing we got above. You can go through and test each of these four vector-vector products, and you'll find out that, yes, indeed, these values are all equivalent. They're just expressed differently and factored differently. So we're going to label this matrix B, and that will be B Hermitian. Okay, so the next part of this slide is going to be a little bit perhaps tedious, and I apologize for that. We're going to prove a lemma and that is, if we have two n by m where n is less than or equal to m matrices A and B, then A Hermitian is equal to B Hermitian if and only if there exists an m by m unitary matrix that we will call Q, such that A is equal to BQ. And just as a reminder, unitary means that QH is equal to the identity matrix. Okay, so let's go through a quick proof of this. We'll start out with assuming that A is equal to BQ. Then we have the AH is equal to Q times QH BH, and the Q's, of course, cancel and give us the identity matrix. So that's just BH. Step 1. That's great. So step 2 is just a little bit trickier. We're going to start with AAH is equal to BBH, and then we'll use the singular value decomposition. So the singular value decomposition gives us something like this. We have U. U is not the same U that we used before to describe the Cholesky decomposition. That was an upper triangular matrix with strictly positive diagonal elements, whereas this U is a unitary matrix. The sigma matrix there is a diagonal matrix, and the zero matrix next to that is, so sigma A will be n by n. Since m is larger, we'll have an n by m minus n zero matrix. And of course we have something similar for B. And These will be non-negative by definition. Okay, so these sigma A and sigma B contain the positive square roots of the eigenvalues of A, AH, and B, BH, respectively. I guess we should make a note of that. And they are called the singular values of A. Okay, since the sigmas contain the positive square roots of the eigenvalues of AAH, and we defined or postulated for this part of the proof that A Hermitian is equal to B Hermitian, then sigma A and sigma B must be equal. They're based on the same eigenvalues. So since AAH equals BBH, sigma A is equal to sigma B. For a singular value decomposition, the U matrices are the right eigenvectors of A Hermitian and B Hermitian in this case. Since A Hermitian is equal to B Hermitian, that means we have UA is equal to UB. Okay, we've got all the pieces in place. We're just trying to define this Q such that A is equal to BQ, so let's go ahead and postulate one. We're going to let Q equal VB times VH Hermitian, VA Hermitian. We can see that when we multiply Q by its Hermitian, that we get a bunch of unitary matrices multiplied together. And since VA is Hermitian, the inner product there is going to be the identity matrix, leaving just VB times VH, which is also the identity matrix. And so we see that Q is indeed, at least QQH is equal to the identity. And we get the same effect for QHQ using the same type of reasoning. We see that that is also the identity matrix. So Q is unitary. Using this Q matrix, we can multiply it by B on the right, and we get UB. So we're using our singular value decomposition version of B times sigma B times VB Hermitian. And now Q is equal to VB VA Hermitian. And since UA is equal to UB and sigma A is equal to sigma B, then we can rewrite this as UA times sigma A, and then of course the VBH VB, V being unitary, VB being unitary, gives us a VH VA Hermitian at the end, which is equal to A. So we've now proven that BQ is equal to A. So we proved it both directions. Let's go through this once again. We defined these, if you will, crazy matrices A and B based on our factorization of P using the Cholesky decomposition into square root P matrices. And these square root P matrices are triangular matrices. And then we have this gamma inverse scalar that we defined in the previous slide or page of notes. And so, although this seems to have come out of the blue, it provides we have now AH and BA, AH, and BBH are equal to the same thing expressed in different ways. Then we went through this long proof, and you can see where this is going. We would really like to express A in terms of B directly. And the first thing we did was we proved that if A is equal to BQ, where Q is a unitary matrix, then we have equality with A Hermitian is equal to B Hermitian. Then we took the other tack and said, if A Hermitian equals B Hermitian, does that mean that A is equal to BQ? And indeed it does. So we are done, and now we will use these in the next lecture to develop our square root RLS algorithm.